Okay, so hello everyone. So today's shirt check, we've got Adidas Red. See, red is best color. Quite relevant as we're talking about hemostasis. This is by special request from NIMAF, so let's get straight into it. So firstly, let's talk about the basics. When we measure clotting time, this is measured through this fibrin clot that we're going to talk about. And hemostasis just means maintaining the blood, keeping it healthy so nothing bad comes in. And that's mainly to do with when you get a wound, we get these platelets coming in to seal it. And that's what we're going to talk about today. So fibrin is formed by the reaction of these platelets, coagulation factors, and other agents, which we'll cover. And firstly, let's talk about platelets and where they come from. So they're developed from the male stem cells, which are then made into these megakaryocytes. And this big structure then breaks down into many little thrombocytes, also known as platelets. So this is controlled by a thrombopoietin. So again, if we look at these stem words, we've got thrombo, so to do with platelets, and poietin to make. And then they take about 10 days to mature, and each megakaryocyte can break down into 4,000 thrombocytes thereabouts. Then we've got the lifespan, which is about 7 to 10 days, and the range in the blood serum is about 150 to 400 times 10 to the 9 per liter. So if we talk about these platelets in a bit more detail, so they've got these alpha granules here, and then the dense granules. So firstly, alpha granules, so they've got these adhesive proteins which make it stick to wounds, as well as these von Willebrand factors which also work with platelet adhesion, and they bind to the collagen in a damaged blood vessel. Then we also got fibrinogen, which we'll talk about later, and works with platelet aggregation, as well as this factor 5 and factor 8 that work in coagulation. Also, as important, we've got these dense granules, which storage for non-metabolic pool of adenine nucleotides, such as ADP and ATP, but it also stores calcium 2+ ions, which are used in fibrinolysis. So if we talk about the liver again very important, and that plays a major role in hemostasis as it produces most of these coagulation factors, proteins, components, and they're all made in these hepatocytes. However, factor 8 is made in liver endothelium, and von Willebrand factors are made again by endothelium or are stored in these platelets. So a quick breakdown of some of the factors. So factor 1 is fibrinogen, factor 2 is prothrombin, and factor 3 is tissue factor. So these factors that we talked about are divided into two groups. So 2, 7, 9, 10 factors. They require vitamin K for metabolism to be made, as well as these calcium 2+ ions for activation. On the other hand, we've got this thrombin group, 1, 5, and 8. So thrombin interacts with them, and they can cause an increase in inflammation. They also increase in pregnancy and with oral contraceptives. Okay, so now let's jump into OneNote and have a quick look of how this primary hemostasis comes about. First thing, we're going to go through the extrinsic pathway. Excuse the handwriting. So what happens firstly? So we've got a wound here, opening, we're bleeding out. So what's the first thing that happens? So platelets arrive because they're in the blood, and they just circle around waiting for the opportunity. And they arrive, and that basically activates the coagulation cascade. So the first thing that happens is we get this tissue factor exposed, so something like that. So that happens when there's an open wound and this tissue factor is exposed. And then what happens is this tissue factor, so say just say it looks like that, just for simplicity's sake. So what happens is this new factor comes in, which is factor 7, and they form a little complex with our special little factor called factor 10. What that basically means is this complex with tissue factor and F7, they activate this factor 10 to become factor 10A. So given that A basically just means it activates it, and then therefore this can now go towards the common pathway. If we look at the intrinsic pathway, so what we have is we have a cascade more in a sense in this pathway where we use loads of tissue factors. So firstly we've got this F7 again, and that activates F11. So this F11, because it becomes activated, it's now 11A. So we've got this 11A which activates F9 to become F9A. And what happens then is we have, again, this complex forming. Obviously it doesn't look like that, but just to make it simpler, we've got F9A, because it's activated, comes together with F8A, and then we have again, ooh, that's a nice color. Then we have again factor 10, which becomes activated into factor 10A. And then that joins together with the other 10A from the other pathway, and then we go onto the common pathway. So now if we move on and go onto the common pathway, so both of the intrinsic and extrinsic make this factor 10A. And what that firstly does is forms a complex with 5A, so factor 5A. So they form a complex here. Let's just get the diagram up again. Not very good at drawing pies. So factor 10A, factor 5A, they form a big complex with our special guest prothrombin. So pro meaning kind of before, such as prokaryotes. And that basically, this complex allows prothrombin to escape into thrombin. This thrombin, what basically then happens is this thrombin allows further activation of platelets. So more platelets come along, they bind, stuff like that. But most importantly, it allows the formation of a special molecule called fibrin. And that's basically formed from the cleavage of fibrinogen, which we talked about is stored in platelets in the granules. And what that basically does, the fibrin, it forms mesh-like strands to connect all the platelets and say red blood cells together. So it forms everything together and it stabilizes the clot. Okay, so now we've had a quick look of how this whole cascade works. Hopefully it wasn't too complicated. But then we get this, we talk about thrombin. So this has a positive feedback loop by activating more factors and more coagulation. However, when that bond is formed and we don't need it anymore, we get this negative feedback and change in the structure and function of thrombin. And now it activates protein C. Also, we have this tissue factor pathway inhibitor, antithrombin, which is the most potent of these inhibitors, as well as protein C and S. So protein C degrades factors in the presence of calcium ions, which are found in those platelets, dense granules. So fibrinolysis, so this is as important as coagulation, as we don't want any clots to forming by an over production of fibrin and platelets bonding together. So this is activated by this TPA released from endothelial cells, and that converts this molecule plasminogen into plasmin, and that is able to break down these peptide bonds in the platelets, as well as digest fibrin and other factors. So how do we measure some of this clotting time? So we can measure the bleeding time and the platelet function, aggregation, as well as this flow cytometry. Then we also have platelet nucleotide assays. However, the main two that are used are APTT, which is activated partial thromboplastin time, which measures the intrinsic pathway, which we talked about, as well as the common pathway when these two come together. Also, we have the prothrombin time, which measures the extrinsic pathway, as well as the common pathway. Though you can measure both of those. However, APTT is seen as more of a sensitive test, as it covers more detail. Quick little definitions: we've got hemophilia, which is bleeding into joints. So heme to do with blood, and such as ophirosis, so to do with joints and bones. And then we've got hematoma, which is basically bruising. So if we talk about some of the diseases that can affect you, so we've got this Bernard-Soulier syndrome, which is autosomal recessive, and the platelets lack this GP1B 9 and 5. So these factors are deficient, and there's no aggregation with ristocetin. We can also get this von Willebrand disease, where we've got a decreased aggregation with ristocetin, and we've got this prolonged breeding time because the platelets aren't able to bind properly to the collagen where the wound is. We also got this Glanzmann's thrombocythemia and the absence of GP2B and 2A. So we've got reduced aggregation with ADP, collagen and adrenaline, and then again prolonged breeding time. We can also get a storage pool disorders. So when we talk about the granules and the platelets, they can be deficient in some of the components there. Then we talk about kind of the main ones and the most common ones. We've got hemophilia A, which is sex-linked, meaning that it's the disorder is covered on the X chromosome, so it's more prevalent in men because we only need one copy of that faulty gene. So we see hemophilia, hematomas, and prolonged APTT, and we basically treat that with factor VIII concentrate because hemophilia is basically deficient in factor VIII. And then we've got hemophilia B, also known as Christmas disease. So a guy called Christmas was the first guy to have it, and then again we treat with concentrate. Also hemophilia C. So as we go down from A to C, kind of becomes less prevalent, and we get milder symptoms. So hemophilia C is deficiency in factor 11. Then we've got factor 12, now associated with abnormal bleeding. However, when we get to factor 13, that's seen severe bleeding tendency, and it's also autosomal recessive. And in this case, the PT and APTT can appear normal, but if we do a special assay for factor 13, they can be seen to be abnormal. But again, it's very rare. We can also get vitamin K deficiency, which stops some of the factors from being developed, and we can also get this hemorrhagic disease of the newborn. So how can we interfere with these disorders to prevent them? So first we can use warfarin. So we've got this which is a coumarin derivative, and it's registered orally, and it's an anticoagulant, so basically stops clotting, and it interferes with this vitamin K metabolism, and that's measured with prothrombin time. Then we also have heparin, which is an intravenous intake and binds to antithrombin and alters its configuration, which enhances its ability to function, and we can measure that with APTT. And both of these need to be measured so the patient doesn't hit a hypocoagulate state. So lastly, we need to be aware of the quality assurance. Basically, we've got the A and R. So we take our mean clotting time and we divide it by the international normal clotting time, and that gives us a ratio, and we can compare across the country. However, it's also important to have this internal. We're using an LJ curve, so having a results on the line and seeing if they deviate, usually 2 standard deviations, either plus or minus. So it's important to check your results when you get loads in from patients to make sure that they're in the normal range. We also have this external NEQAS. Don't remember what it stands for, but it basically allows to, again, compare your means with other hospitals in the country. So yeah, that was a quick summary of hemostasis. Hope I helped out, and yeah, see you in the next video. And don't forget to like and subscribe. Check the link if you want any free trials or books. See you in the next one. Cheers.